Right now, as you're watching this video, you're surrounded by an invisible orchestra. Every second, your body is being penetrated by cosmic rays that traveled millions of years to reach you. Radio waves from distant galaxies are washing over you like invisible tides. The very atoms in your body are vibrating to frequencies that originated in the heart of dying stars. And all of this is creating a symphony so vast, so ancient, and so beautiful that most people will never know it exists. But what if I told you that space isn't the silent void you've been told it is? What if I told you that the universe has been singing to us this entire time, and we're only just beginning to learn how to listen? Close your eyes for 30 seconds after this video starts. I want you to imagine something impossible. Imagine hearing the birth cry of a star being born in a nebula 3,000 light-years away. Imagine the deep, rhythmic pulse of a neutron star spinning 30 times per second, creating a cosmic lighthouse that's been flashing for millions of years. Imagine the haunting melody of two black holes, each containing the mass of 30 suns, as they spiral toward each other at half the speed of light before merging in a collision so violent it sends ripples through the very fabric of space and time. This isn't science fiction. This is science fact. And today, we're going to take you on an auditory journey through the cosmos that will forever change how you think about the universe around you. We're going to explore the hidden symphony that fills every cubic meter of space, from the quantum whispers of dark matter to the thunderous roar of galactic collisions that shake the foundations of reality itself. But first, I need to know something. Drop a comment right now and tell me where you're watching this from and what time it is there. Are you watching from New York at midnight? Tokyo during your lunch break? Maybe you're in London on a rainy afternoon, or perhaps you're somewhere I've never even heard of. I want to know because what you're about to learn connects every single one of us to every other place in the universe in ways that will absolutely blow your mind. The same cosmic radiation that's hitting you right now has traveled across billions of years and billions of miles to reach exactly where you are, exactly when you are. You are literally made of stardust, and you're about to hear the songs that those stars sang as they died to create you. The Silent Symphony. For over 400 years, we've been told that space is the ultimate vacuum. The perfect silence. The absolute void where no sound can travel because there's no air, no medium, no substance to carry vibrations from one place to another. School textbooks still teach this. Movies still perpetuate this myth with their dramatic explosions that should be completely silent in the vacuum of space. But here's what they don't teach you in school. The universe is actually filled with invisible matter and energy that can carry information, vibrations, and yes, even sound-like phenomena across vast distances. We're not talking about sound as you know it, the compression waves that travel through air and reach your eardrums. We're talking about something far more fundamental, far more beautiful, and far more mysterious. Every single object in space, from the tiniest asteroid to the most massive galaxy, is constantly emitting electromagnetic radiation. These are waves of energy that travel at the speed of light, carrying information about their source across billions of years and billions of miles. Scientists have developed ways to convert these electromagnetic signals into audio frequencies that human ears can actually hear. It's like having a universal translator for the language of the cosmos. Think about your radio for a moment. When you tune into your favorite station, you're detecting electromagnetic waves that were converted from sound waves at the radio station, transmitted through the air, and then converted back into sound waves by your radio's speakers. What we're doing with space sounds is remarkably similar, except instead of converting someone's voice or music, we're converting the electromagnetic signatures of stars being born, black holes colliding, and galaxies spinning through space. But there's something even more incredible happening here. Space isn't actually empty. Between the stars, between the planets, between the galaxies themselves, there's a thin soup of particles, magnetic fields, an energy that scientists call the interstellar medium. It's incredibly sparse. In most places, there might be only 1 atom per cubic centimeter, which is a better vacuum than anything we can create on Earth. But it's there, and it can carry vibrations across vast distances. When massive cosmic events occur, supernovas, stellar collisions, the formation of new stars, they send shock waves rippling through this thin cosmic soup. These shock waves can travel for thousands of light years, carrying the sound of these events across the galaxy. They're like cosmic thunder following cosmic lightning, except this thunder can echo for millions of years. What's truly mind-bending is that some of the sounds we're detecting today originated from events that happened before our solar system even existed. The light and radio waves reaching us now left their source when the Milky Way galaxy was younger, when different stars ruled the sky, when the very atoms that make up your body were still trapped inside massive stars waiting to be released by supernova explosions. Scientists at institutions like NASA, the European Space Agency, and radio observatories around the world have been collecting these cosmic sounds for decades. They use massive radio telescopes, space-based instruments, and incredibly sensitive detectors to capture electromagnetic signals from across the universe. Then, using sophisticated computer programs, they convert these signals into audio frequencies that reveal the hidden symphony of space. Some of these sounds are rhythmic, like cosmic heartbeats. Others are chaotic, like the static of cosmic storms. Some are hauntingly beautiful melodies that sound almost musical, while others are deep, rumbling drones that seem to come from the very foundations of reality itself. Each sound tells a story about its source, the composition of a star, the magnetic field of a planet, the rotation speed of a pulsar, or the approach of a massive asteroid. The technology to detect these cosmic sounds has advanced dramatically in recent years. New space missions are equipped with instruments specifically designed to listen to the universe. The Parker Solar Probe, launched in 2018, has been sending back audio recordings of the solar wind as it flies closer to the Sun than any spacecraft in history. The Juno mission to Jupiter has captured the sounds of the planet's massive magnetic field and its interactions with the solar wind. The Cassini spacecraft recorded the sounds of Saturn's rings for over a decade before its mission ended. But perhaps the most incredible realization is this: these cosmic sounds aren't just random noise. They're information. They're data about the universe's structure, its history, and its future. By learning to listen to the universe, we're developing a completely new sense organ for understanding reality. We're becoming cosmic archaeologists, digging through layers of sound to uncover the history written in the electromagnetic signatures of distant worlds. Every wave that reaches us is like a message in a bottle, thrown into the cosmic ocean billions of years ago by events so massive and energetic that they defy human comprehension. Stars exploding with the force of billions of nuclear bombs. Black holes with gravitational fields so strong they bend light and time itself. Galaxies colliding and merging over hundreds of millions of years. All of these events leave their signatures in the cosmic soundtrack that surrounds us. The stellar chorus. Let's start our journey with the stars themselves. Those massive nuclear furnaces that light up the darkness and forge the elements that make life possible. If you thought stars were just silent balls of hot gas, prepare to have your mind completely transformed. Every star in the universe is essentially a massive musical instrument, vibrating with frequencies that depend on its size, composition, age, and internal structure. These vibrations create what scientists call stellar oscillations. Essentially, stars are ringing like bells, and we've learned how to listen to their songs. Our own sun is perhaps the best-studied stellar musician in the universe. The entire surface of the sun vibrates with millions of different oscillation modes, creating a complex symphony that scientists have been studying for decades. These solar oscillations have frequencies ranging from deep, slow rumbles that take hours to complete one cycle, to rapid high-pitched vibrations that oscillate several times per minute. The sound of the sun is surprisingly deep and rumbling, like a massive organ pipe or a distant earthquake that never ends. When converted to audio frequencies that human ears can detect, solar oscillations sound like a combination of wind, distant thunder, and the deep hum of massive machinery. It's both soothing and slightly ominous, like the breathing of some cosmic giant. But here's what makes this even more incredible. By analyzing these solar sounds, scientists can actually see inside the sun. Just like doctors use ultrasound to see inside the human body, astronomers use helioseismology, the study of solar sounds, to map the sun's interior structure. We can detect the rotation rate at different depths, identify the boundaries between different layers, and even track the movement of material from the sun's core to its surface. The sun's core, where nuclear fusion converts hydrogen into helium and releases the energy that powers our entire solar system, has its own distinct acoustic signature. The incredible temperatures and pressures at the sun's center create unique oscillation patterns that carry information about fusion rates, energy transport, and the fundamental physics of stellar cores. We're literally listening to the nuclear fire that makes life on Earth possible. Different types of stars create completely different soundscapes. Red giant stars, which are massive stars in the later stages of their lives, produce deep, slow oscillations that sound like cosmic whale songs. These stars have expanded to hundreds of times their original size, and their enormous, tenuous atmospheres vibrate with periods that can last for days or weeks. White dwarf stars, which are the ultra-dense remnants of stars like our Sun, create rapid, high-pitched oscillations that sound almost like cosmic wind chimes. These stellar corpses are so dense that a teaspoon of white dwarf material would weigh as much as a car, and their oscillations can complete hundreds of cycles per second. But perhaps the most dramatic stellar musicians are neutron stars, particularly a special class called pulsars. Neutron stars are the collapsed cores of massive stars that exploded as supernovas. They're incredibly dense. Imagine compressing the mass of our entire sun into a sphere only about 12 miles across. A single teaspoon of neutron star material would weigh about 1 billion tons. Pulsars are neutron stars that spin rapidly while emitting beams of radiation from their magnetic poles. As they rotate, these beams sweep across space like cosmic lighthouses, and when the beam points toward Earth, we detect a brief pulse of radiation. The fastest known pulsar spins over 700 times per second, creating a rapid-fire beat that sounds like a cosmic machine gun. The sound of a pulsar is unlike anything else in the universe. It's a perfect, metronomic rhythm that can maintain its timing for millions of years. Some pulsars are so precise that they rival atomic clocks as the most accurate timekeepers in the universe. The rhythmic pulses create audio patterns that range from slow, steady heartbeats to rapid-fire percussion that would challenge the fastest drummer on Earth. What makes pulsar sounds even more remarkable is their stability over time. The crab pulsar, created by a supernova explosion that was observed by Chinese astronomers in 1054 AD, has been spinning down gradually over the past 1,000 years, but its rhythm remains incredibly precise. By monitoring changes in pulsar timing, scientists can study fundamental physics, including the effects of gravitational waves and the structure of space-time itself. Binary star systems create even more complex musical arrangements. When two stars orbit around each other, their gravitational interaction creates unique acoustic signatures that depend on their masses, orbital periods, and the distance between them. Some binary systems have orbital periods of hours, creating rapid, rhythmic variations in their electromagnetic output. Others take centuries to complete one orbit, producing slow, sweeping changes that require decades of observation to detect. When binary stars are close enough, material can flow from one star to the other, creating accretion disks and stellar winds that produce their own distinctive sounds. The material spiraling into these disks can reach temperatures of millions of degrees, emitting X-rays and other high-energy radiation that creates complex, chaotic audio patterns when converted to sound. Some of the most violent stellar sounds come from stellar flares and coronal mass ejections. When magnetic field lines in a star's atmosphere suddenly reconnect, they can release energy equivalent to billions of nuclear bombs in a matter of minutes. These stellar explosions create shock waves that ripple through the star's atmosphere and surrounding space, producing audio signatures that sound like cosmic explosions, crackling fires, and electrical discharges. Variable stars add another layer to the stellar symphony. These stars change their brightness over time due to internal processes, stellar pulsations, or interactions with companion objects. Cepheid variable stars, which are massive stars that pulsate regularly, create rhythmic audio patterns that sound like cosmic breathing or the slow beating of enormous hearts. The timing of these pulsations is so regular that astronomers use Cepheid variables as standard candles to measure distances across the universe. Young stars, still in the process of formation, create some of the most chaotic and energetic stellar sounds. Protostars are surrounded by disks of gas and dust that spiral inward while magnetic fields channel material along their axes, creating powerful jets that can extend for light years. The turbulence in these forming stellar systems creates complex audio patterns that sound like cosmic storms, with rapid changes in pitch, rhythm, and intensity. Brown dwarfs, sometimes called failed stars, because they're not massive enough to sustain nuclear fusion, produce their own unique soundscapes. These objects are larger than planets but smaller than stars, and they emit most of their energy as infrared radiation. When converted to audio, brown dwarfs often sound like deep, rumbling drones with occasional bursts of higher frequency activity. As we listen to this stellar chorus, we're not just hearing random noise. Each sound carries specific information about stellar physics, stellar evolution, and the fundamental processes that govern how stars live and die. The frequency patterns tell us about stellar masses, ages, compositions, and internal structures. The timing variations reveal rotation rates, magnetic field strengths, and orbital mechanics. Perhaps most remarkably, some stellar sounds carry information about the formation of planets. When planets form around young stars, they create gaps in the surrounding disk of material, and these gaps produce distinctive acoustic signatures. By listening carefully to the sounds of young stellar systems, astronomers can detect the presence of forming planets before they're visible in any other way. The stellar symphony is constantly evolving. As stars age, their sounds change, reflecting the nuclear processes happening in their cores, the evolution of their internal structures, and the gradual changes in their magnetic fields and rotation rates. By monitoring stellar sounds over time, we're creating a time-lapse movie of stellar evolution that reveals how stars transform over millions and billions of years. What's truly awe-inspiring is the realization that every element in your body, the calcium in your bones, the iron in your blood, the oxygen you breathe, was forged inside stars and dispersed by the very stellar explosions whose sounds we can now detect. You are literally made of material that once rang with the acoustic signatures of stellar cores, and those same sounds are still echoing through the universe today. Have you ever wondered what it would sound like to fly through a nebula where new stars are being born? I want you to take a moment and imagine that experience. Drop a comment and describe what you think it would sound like to travel at the speed of light through a stellar nursery, where massive clouds of gas and dust are slowly condensing into the next generation of cosmic musicians. What sounds do you think you'd hear as new stars ignite their nuclear fires for the first time? Galactic echoes. Now let's expand our cosmic perspective from individual stars to entire galaxies. vast collections of hundreds of billions of stars, along with dark matter, gas clouds, and the mysterious massive objects that lurk at galactic centers. If you thought the sounds of individual stars were impressive, the audio signatures of entire galaxies will absolutely transform your understanding of the universe's scale and complexity. Our home galaxy, the Milky Way, is constantly humming with electromagnetic activity. Radio telescopes pointed toward the galactic center detect a complex symphony of overlapping signals from millions of stars, vast clouds of ionized gas, and a supermassive black hole that anchors our entire galactic system. When these signals are converted to audio, the Milky Way sounds like a vast, living organism, breathing, pulsing, and constantly evolving. The rotation of our galaxy creates its own distinctive audio signature. The Milky Way rotates differentially, meaning that stars closer to the galactic center orbit faster than stars farther out. This differential rotation creates spiral density waves that propagate through the galactic disk like ripples on a cosmic pond. These waves compress and rarefy the interstellar medium, creating acoustic patterns that can be detected by sensitive radio telescopes. The spiral arms of our galaxy are essentially cosmic traffic jams where stars, gas clouds, and magnetic fields bunch up as they flow through the galactic disk. As material moves into and out of these spiral arms, it creates distinctive acoustic signatures that reveal the galaxy's structure, rotation rate, and the distribution of mass throughout the galactic disk. The sounds of spiral density waves are deep and rhythmic, like the slow breathing of some enormous cosmic entity. But the most dramatic galactic sounds come from the supermassive black holes that exist at the centers of most galaxies. These objects contain millions or billions of times the mass of our Sun compressed into regions smaller than our solar system. The gravitational fields around these black holes are so intense that they accelerate nearby material to significant fractions of the speed of light, creating some of the most energetic phenomena in the universe. Active galactic nuclei. Galaxies with supermassive black holes that are actively consuming material produce incredibly powerful jets of high-energy particles that extend for thousands of light-years beyond the galaxy itself. These jets emit radio waves, X-rays, and gamma rays that create complex audio patterns when converted to sound. The audio signature of an active galactic nucleus sounds like a combination of a massive waterfall, electrical arcing, and the roar of a cosmic blowtorch. The material spiraling into a supermassive black hole forms what's called an accretion disk, a flat, rotating disk of superheated gas and plasma that can reach temperatures of millions of degrees. The turbulence in these accretion disks creates chaotic audio patterns that change rapidly over time. Material in the inner regions of the accretion disk orbits the black hole several times per hour, while material in the outer regions might take days or weeks to complete one orbit. This creates complex, layered audio patterns with multiple overlapping rhythms and frequencies. Some supermassive black holes produce regular, rhythmic variations in their output that sound almost musical. These oscillations might be caused by instabilities in the accretion disk, precession of the jets, or interactions between the black hole's magnetic field and the surrounding material. The timing of these oscillations provides crucial information about the black hole's mass, rotation rate, and the physics of matter under extreme gravitational conditions. Galaxy collisions create some of the most spectacular sounds in the universe. When two galaxies approach each other, their gravitational interaction triggers massive bursts of star formation, distorts their spiral structures, and can activate dormant supermassive black holes. The audio signature of a galaxy collision spans millions of years and includes the sounds of shock waves propagating through intergalactic gas, the gravitational waves produced by merging black holes, and the electromagnetic signatures of millions of new stars being born simultaneously. The ongoing collision between our Milky Way and the smaller Magellanic Clouds produces distinctive acoustic signatures that astronomers have been studying for decades. As the Magellanic Clouds orbit around our galaxy, their gravitational interaction strips away gas and stars, creating vast streams of material that extend across hundreds of thousands of light years. The turbulence in these tidal streams creates audio patterns that reveal the distribution of dark matter in our local galactic neighborhood. But perhaps the most mind-bending galactic sounds come from dark matter interactions. Dark matter makes up about 85% of all matter in the universe, but it doesn't emit, absorb, or reflect electromagnetic radiation, making it essentially invisible to traditional telescopes. However, dark matter does interact gravitationally with normal matter, and these interactions can produce subtle acoustic signatures in the cosmic microwave background radiation and in the distribution of galaxies across the universe. Computer simulations of dark matter structure formation predict that dark matter should create vast web-like networks of filaments connecting galaxy clusters across billions of light years. When normal matter falls into these dark matter structures, it should create shock waves and acoustic oscillations that could, in principle, be detected by sensitive instruments. Some researchers believe they've already detected the faint acoustic signatures of dark matter streams in radio telescope data, though these claims remain highly controversial. Galaxy clusters, groups of hundreds or thousands of galaxies held together by gravity, produce their own unique soundscapes. The space between galaxies in a cluster is filled with incredibly hot gas that emits X-rays and radio waves. This intercluster medium has temperatures of tens of millions of degrees and densities millions of times lower than the best vacuum achievable on Earth, yet it contains more mass than all the visible stars in all the galaxies combined. The movement of galaxies through this hot intracluster gas creates bow shocks and wake patterns similar to what happens when a boat moves through water, except these cosmic bow shocks extend for millions of light years and persist for hundreds of millions of years. The acoustic signatures of these interactions reveal the speeds at which galaxies move through clusters, the distribution of dark matter, and the physics of plasma under extreme conditions. Some galaxy clusters show evidence of massive explosions caused by supermassive black holes in their central galaxies. These explosions create cavities in the hot intracluster gas that can be larger than entire galaxies. The formation and evolution of these cavities produces distinctive acoustic signatures that sound like cosmic echoes reverberating through intergalactic space. Radio galaxies. Galaxies with supermassive black holes that produce enormous radio-emitting jets create some of the largest and most long-lasting acoustic structures in the universe. The jets from some radio galaxies extend for millions of light years and remain active for hundreds of millions of years, creating vast bubbles of energetic particles that interact with magnetic fields throughout intergalactic space. The edges of these radio bubbles act like cosmic membranes that can resonate with acoustic waves propagating through the intergalactic medium. Some researchers have suggested that these resonating radio bubbles might act like gigantic musical instruments, producing very low-frequency oscillations that could, in principle, be detected by future space-based gravitational wave detectors. What's particularly fascinating is that galaxies seem to have acoustic signatures that depend on their age, mass, and evolutionary history. Young, star-forming galaxies produce chaotic, energetic soundscapes dominated by the noise of rapid star formation and supernova explosions. Older, more evolved galaxies tend to produce more stable, rhythmic patterns dominated by the sounds of old stellar populations and occasionally active supermassive black holes. Elliptical galaxies, which are typically older and contain mostly old stars, produce relatively quiet audio signatures dominated by the low-frequency emissions of aging stellar populations. Spiral galaxies like our own Milky Way produce more complex soundscapes that include the rhythmic patterns of spiral density waves, the chaos of ongoing star formation, and the periodic signals from various types of variable stars. Irregular galaxies, which have chaotic structures often caused by gravitational interactions or galaxy mergers, produce highly variable and unpredictable audio patterns that change rapidly over time. These galaxies often contain regions of intense star formation that create bursts of high-energy electromagnetic radiation, followed by quieter periods when star formation rates decline. The study of galactic acoustics is revealing fundamental information about how galaxies form, evolve, and interact over cosmic time. By comparing the audio signatures of galaxies at different distances, which correspond to different points in cosmic history, astronomers are creating a timeline of galactic evolution that extends back to within a few 100 million years of the Big Bang. Some of the most distant galaxies we can observe, whose light has been traveling toward us for over 13 billion years, produce audio signatures that are dramatically different from nearby galaxies. These ancient galaxies were forming during a period when the universe was much smaller, denser, and more chaotic than it is today. Their sounds carry information about the conditions in the early universe and the first generations of stars and galaxies. Think about this for a moment. Every time you listen to these galactic sounds, you're hearing the acoustic signatures of events that happened billions of years ago, when the universe was fundamentally different from what we see today. The radio waves reaching us now left their source galaxies before our solar system existed, before complex life evolved on Earth, before the Milky Way had settled into its current spiral structure. I want you to imagine something incredible. Picture yourself floating in the space between galaxies, in the vast cosmic web of dark matter and hot gas that connects all the galaxies in the universe. What do you think you would hear in that seemingly empty space? Take a moment to comment below and describe what you imagine the sounds of intergalactic space might be like. Would it be completely silent, or do you think there might be faint echoes of ancient cosmic events still reverberating through the darkness? The primordial hum. We've journeyed from the songs of individual stars to the symphonies of entire galaxies. But now we're going to explore the most ancient and fundamental sound in the universe, the acoustic signature of creation itself. What we're about to discover will fundamentally change how you think about the Big Bang, the origin of the universe, and your connection to the cosmic story that began 13.8 billion years ago. For decades, scientists have studied the cosmic microwave background radiation, the afterglow of the Big Bang that fills every cubic centimeter of space. This radiation provides a snapshot of the universe when it was only 380,000 years old, long before the first stars formed, before the first galaxies condensed out of the primordial darkness. But here's what most people don't realize. This ancient radiation contains acoustic information that allows us to literally hear the sound of the universe being born. The early universe wasn't the chaotic explosion that most people imagine when they hear Big Bang. Instead, it was filled with acoustic waves, sound waves propagating through the hot, dense plasma that filled all of space. These primordial sound waves were created by tiny quantum fluctuations in the fabric of space-time itself, fluctuations that were stretched to cosmic proportions during the brief period of cosmic inflation that occurred in the first fraction of a second after the Big Bang. Think of the early universe as a vast musical instrument, a cosmic organ pipe filled with hot plasma that could support acoustic oscillations. Just like sound waves in air, these cosmic acoustic waves had specific frequencies, wavelengths, and amplitudes that depended on the properties of the primordial plasma. The fundamental frequency of this cosmic instrument was determined by the size of the observable universe at that time, the density of matter and energy, and the speed of sound in the primordial plasma. When scientists convert the patterns in the cosmic microwave background radiation into audio frequencies, they discover something remarkable. The universe began not with a chaotic bang, but with a deep, resonant hum. This primordial sound is incredibly low frequency, about 57 octaves below middle C on a piano. It's a sound so deep that it would be completely inaudible to human ears. But when shifted up to audible frequencies, it reveals the acoustic signature of creation itself. The cosmic microwave background contains detailed information about these primordial acoustic oscillations. Scientists can identify the fundamental frequency and its harmonics, revealing how sound waves of different wavelengths propagated through the early universe. The pattern of these acoustic peaks provides precise measurements of the universe's composition, age, geometry, and ultimate fate. What makes this even more incredible is the realization that the large-scale structure we see in the universe today, the distribution of galaxies, galaxy clusters, and vast cosmic voids, is directly descended from these primordial sound waves. The acoustic oscillations in the early universe created regions of slightly higher and lower density, and these density variations served as the seeds from which all cosmic structure eventually grew. The sound of the Big Bang reveals that the universe is composed of approximately 5% ordinary matter, 27% dark matter, and 68% dark energy. These precise measurements come from analyzing the acoustic signatures preserved in the cosmic microwave background radiation. We're literally using the sound of creation to determine what the universe is made of. But the primordial acoustic story doesn't end with the cosmic microwave background. Those same sound waves that we detect in the early universe continued to propagate through space long after the cosmic microwave background was formed. As the universe expanded and cooled, these acoustic oscillations left their imprint in the distribution of matter throughout the cosmos. Modern galaxy surveys can detect the acoustic signatures of these primordial sound waves in the current distribution of galaxies across the universe. The pattern is called baryon acoustic oscillations, and it provides a standard ruler for measuring cosmic distances and the expansion rate of the universe. We're using the echo of the Big Bang sound to map the geometry of spacetime itself. The wavelength of these baryon acoustic oscillations is about 500 million light-years, roughly the distance sound could travel in the primordial plasma before the universe became transparent. This distance scale appears as a subtle peak in the statistical distribution of galaxies, like a cosmic fingerprint left by the sound waves of creation. Recent advances in gravitational wave astronomy have opened up entirely new ways of listening to the primordial universe. The LIGO and Virgo gravitational wave detectors have successfully detected the sounds of black hole mergers and neutron star collisions, but future space-based gravitational wave telescopes might be able to detect gravitational waves produced during cosmic inflation itself. If such primordial gravitational waves exist and can be detected, they would provide direct acoustic information about the first tiny fraction of a second after the Big Bang, long before the universe became transparent and started emitting the cosmic microwave background radiation. This would be like having a recording of the universe's birth cry, captured in the stretching and compression of space-time itself. The physics of the primordial universe was so extreme that it challenges our understanding of fundamental laws. During the first moment after the Big Bang, temperatures exceeded 10 to the power of 32 degrees Kelvin, and the density of the universe was greater than 10 to the power of 94 times the density of water. Under these conditions, the normal concepts of matter, energy, space, and time break down, and we need new physics to understand what was happening. Some theoretical models suggest that the universe might have undergone multiple phases of acoustic evolution during its earliest moments. If the universe experienced a period of cosmic inflation, as most cosmologists believe, then the acoustic properties of spacetime itself might have changed dramatically during the transition from the inflationary epoch to the hot Big Bang phase. These phase transitions could have produced their own distinctive acoustic signatures. gravitational waves with specific frequency patterns that encode information about the fundamental physics of the inflationary process. Future gravitational wave telescopes might be able to detect these signals and reveal details about the universe's birth that are completely inaccessible through any other means. The primordial acoustic oscillations also provide crucial information about the nature of dark matter and dark energy. The speed of sound in the primordial plasma was affected by the interactions between ordinary matter, dark matter, and radiation. By precisely measuring the acoustic patterns in the cosmic microwave background, scientists can test different theories about what dark matter is and how it interacts with ordinary matter. Some exotic dark matter theories predict that dark matter particles should have produced their own acoustic signatures in the early universe, signatures that would appear as subtle modifications to the standard acoustic patterns. So far, no such modifications have been detected, which places strict limits on the properties of dark matter particles. Dark energy, the mysterious force causing the universe's expansion to accelerate, also affects the acoustic patterns we observe. The acoustic peaks in the cosmic microwave background provide some of the strongest evidence for dark energy's existence, and help determine its properties. The sound of the Big Bang is literally telling us about the ultimate fate of the universe. What's perhaps most mind-blowing is the realization that you can hear echoes of the Big Bang in everyday life. The static you hear when you tune a radio between stations contains a small component, about 1%, that comes directly from the cosmic microwave background radiation. You're literally listening to the afterglow of creation every time you hear radio static. The cosmic microwave background radiation is perfectly uniform across the entire sky to a precision of better than 1 part in 100,000, but the tiny variations that do exist contain an enormous amount of information about the universe's properties and history. These variations represent the acoustic fingerprint of the primordial sound waves that gave birth to all cosmic structure. Advanced computer simulations can now model the propagation of these primordial sound waves with incredible precision, predicting exactly what patterns should appear in the cosmic microwave background based on different theories about the early universe. The agreement between these predictions and the actual observed patterns is one of the greatest triumphs of modern cosmology. But there are still mysteries hidden in the primordial acoustic data. Some features of the cosmic microwave background don't perfectly match the predictions of standard cosmological models. These anomalies are subtle, but they might indicate that our understanding of the early universe is incomplete, or that new physics was operating during the primordial epoch. Future missions to study the cosmic microwave background with even greater precision might reveal additional acoustic signatures that could revolutionize our understanding of fundamental physics. We might discover evidence for extra dimensions, exotic particles, or completely new physical phenomena that operated during the universe's first moments. The study of primordial acoustics is also revealing information about the global geometry of the universe. The acoustic patterns in the cosmic microwave background provide precise measurements of the universe's curvature, confirming that space is flat to within experimental uncertainty. This geometric information comes directly from analyzing how sound waves propagated through the primordial cosmos. As we contemplate the primordial hum of the Big Bang, we're confronting one of the most profound questions in science. Why does anything exist at all? The acoustic signatures of the early universe suggest that our cosmos emerged from quantum fluctuations in a vacuum, that everything we see around us, including ourselves, originated from the spontaneous creation of sound waves in empty space. The next time you experience a moment of perfect silence, remember that you're never truly in silence. The cosmic microwave background radiation is constantly washing over you, carrying the acoustic signature of the universe's birth. You're immersed in the afterglow of creation itself, surrounded by the fading echoes of the primordial sound that gave birth to stars, galaxies, planets, and ultimately to you. Before we continue to explore what the future might hold for cosmic acoustics, I want to ask you something that might seem impossible to answer. If you could travel back in time to witness the Big Bang firsthand, what do you think it would actually sound like? Not the deep hum we detect today, but the actual acoustic experience of being present during the first moments of creation. Share your thoughts in the comments. Would it be a whisper or a roar? Musical or chaotic? What words would you use to describe the sound of everything beginning? Future harmonies. As we stand at the threshold of a new era in cosmic acoustics, the technology that's being developed and deployed right now will revolutionize our ability to listen to the universe in ways that would have seemed like pure science fiction just a generation ago. What we've discovered about cosmic sounds so far is merely the opening movement of a symphony that will unfold over the coming decades, revealing aspects of reality that we can barely imagine today. The future of cosmic sound detection begins with gravitational waves, ripples in the fabric of space-time itself that carry acoustic information about the most violent and energetic events in the universe. The LIGO and Virgo detectors have already opened our ears to the sounds of black hole mergers and neutron star collisions. But these ground-based instruments can only detect gravitational waves in a narrow frequency range, roughly equivalent to the audio frequencies that human ears can hear. The next generation of gravitational wave detectors will extend our hearing into entirely new frequency ranges, revealing cosmic sounds that are currently beyond our detection capabilities. The Laser Interferometer Space Antenna, or LISA, scheduled for launch in the 2030s, will consist of 3 spacecraft flying in formation millions of kilometers apart, creating a gravitational wave detector larger than Earth itself. LISA will be sensitive to much lower frequency gravitational waves than ground-based detectors can observe. These low-frequency waves carry information about supermassive black hole mergers, the inspiral of stellar mass objects into supermassive black holes, and potentially even gravitational waves left over from cosmic inflation. We're about to hear the universe's deepest bass notes for the first time. But the real revolution will come from space-based telescopes specifically designed to detect electromagnetic signals from exoplanets, worlds orbiting other stars. The James Webb Space Telescope has already begun detecting atmospheric compositions of distant exoplanets by analyzing the light filtering through their atmospheres as they transit in front of their host stars. Future missions will extend this capability to detect potential biosignatures and even technosignatures, evidence of technological civilizations. What's truly exciting is that some exoplanets might have atmospheric compositions or magnetic field interactions that produce distinctive electromagnetic signatures when converted to audio. We might discover exoplanets with global aurora systems that create rhythmic radio patterns, or worlds with atmospheric chemistry so exotic that their electromagnetic emissions sound unlike anything in our solar system. The possibility of detecting artificial signals from technological civilizations adds an entirely new dimension to cosmic acoustics. The search for extraterrestrial intelligence, or SETI, has been listening for artificial radio signals for decades, but future instruments will have unprecedented sensitivity and the ability to detect much more subtle forms of technological activity. Advanced alien civilizations might communicate using gravitational waves, modulated neutrino beams, or electromagnetic signals in frequency ranges we haven't yet explored thoroughly. They might use the natural electromagnetic emissions of their star systems as carriers for information, creating artificial modulations in stellar oscillations or radio emissions that would be detectable across interstellar distances. Even more intriguingly, truly advanced civilizations might engage in large-scale engineering projects that would produce distinctive acoustic signatures detectable from thousands of light-years away. Dyson spheres, hypothetical megastructures that could capture most of a star's energy output, would create characteristic infrared signatures that might include temporal variations resembling technological activity. The concept of stellar engineering extends beyond energy collection to include modifications of stellar oscillations themselves. An incredibly advanced civilization might learn to manipulate their star's magnetic field or internal structure to create artificial acoustic patterns, essentially turning their entire star into a cosmic musical instrument capable of transmitting complex information across the galaxy. Closer to home, the increasing sophistication of our solar system exploration missions is revealing new types of cosmic sounds within our own cosmic neighborhood. The Parker Solar Probe has already detected acoustic waves in the solar wind that had never been observed before, including Whistler waves, ion acoustic waves, and electromagnetic fluctuations that create complex audio patterns when converted to sound. Future missions to the outer planets will carry instruments capable of detecting acoustic phenomena in environments we've never explored before. Europa, Jupiter's ice-covered moon, might have acoustic activity in its subsurface ocean caused by tidal heating, geothermal vents, or even biological processes. Titan, Saturn's largest moon, has a thick atmosphere and liquid hydrocarbon lakes that could support acoustic waves remarkably similar to sound waves on Earth. The advancement of quantum sensors is opening up entirely new possibilities for detecting cosmic sounds. Quantum gravitational wave detectors could eventually achieve sensitivities billions of times greater than current instruments, potentially detecting gravitational waves from the Big Bang itself, individual stellar collapse events in distant galaxies, or even the quantum mechanical fluctuations of space-time at the smallest scales. Quantum communication networks between Earth and space-based instruments could enable coordinated observations across the solar system, creating gravitational wave detectors with baselines measured in astronomical units. Such a network could detect gravitational waves with wavelengths comparable to the size of planetary orbits, revealing acoustic information about cosmic structures and events at scales we've never before been able to probe. The development of artificial intelligence and machine learning is revolutionizing our ability to identify and interpret cosmic sounds. Modern AI systems can analyze vast databases of astronomical signals, identifying patterns and anomalies that human researchers might miss. These systems are already discovering new types of variable stars, detecting subtle gravitational wave signals buried in noise, and identifying previously unknown sources of radio emissions. Future AI systems will be capable of real-time analysis of cosmic acoustic data from hundreds of different instruments simultaneously, creating a global network of cosmic sound detection that operates continuously. These systems might identify new classes of cosmic phenomena, detect the earliest warning signs of gravitational wave events, or even recognize the signatures of unknown physics in the acoustic patterns of distant cosmic objects. The integration of multiple types of cosmic sound detection, electromagnetic, gravitational wave, neutrino, and potentially even exotic particle detections, will create a truly multi-messenger approach to cosmic acoustics. When a major cosmic event occurs, like a supernova explosion or black hole merger, future instruments will detect the acoustic signatures across multiple different types of radiation and particles, creating a comprehensive acoustic portrait of the event. This multi-messenger approach has already proven incredibly powerful with the detection of gravitational waves, electromagnetic radiation, and neutrinos from the same neutron star merger in 2017. Future detections will include additional messengers and much more sensitive instruments, creating acoustic reconstructions of cosmic events with unprecedented detail and accuracy. The possibility of detecting cosmic strings, hypothetical one-dimensional defects in space-time left over from the early universe, represents one of the most exotic frontiers in cosmic acoustics. If cosmic strings exist and occasionally snap or oscillate, they would produce distinctive gravitational wave patterns unlike anything else in the universe. These signals would carry information about physics at energy scales far beyond anything achievable in terrestrial laboratories. Dark matter detection experiments might eventually reveal that dark matter particles interact with each other or with ordinary matter in ways that produce acoustic signatures. If dark matter undergoes annihilation reactions or experiences collective oscillations, these processes might produce electromagnetic or gravitational wave signals detectable by future instruments. The study of cosmic acoustics is also driving the development of new theoretical frameworks for understanding space, time, matter, and energy. The acoustic properties of black hole event horizons, the propagation of sound in curved spacetime, and the relationship between quantum mechanics and gravitational waves are all active areas of research that could lead to revolutionary discoveries about the fundamental nature of reality. Some theoretical physicists speculate that spacetime itself might have acoustic properties at the quantum scale, that the vacuum of empty space might support acoustic oscillations analogous to sound waves in a material medium. If such quantum acoustic phenomena exist, they might be detectable through their effects on gravitational waves or other cosmic signals. The concept of cosmic archaeology through acoustic detection is becoming increasingly sophisticated. By analyzing the acoustic signatures of ancient cosmic events, we can reconstruct the history of the universe with unprecedented temporal and spatial resolution. Future surveys might detect acoustic echoes from events that happened billions of years ago, creating a detailed acoustic timeline of cosmic evolution. What's particularly exciting is the possibility that cosmic acoustic archaeology might reveal evidence of previous universes or cosmic cycles. Some cosmological theories predict that our universe went through multiple phases of expansion, contraction, and rebirth. If such cycles occurred, they might have left acoustic fingerprints in the cosmic microwave background radiation or in gravitational wave signals that we haven't yet learned how to detect. The democratization of cosmic sound detection through citizen science projects and amateur astronomy is creating a global community of cosmic acoustic researchers. Projects like Einstein at Home allow volunteers to contribute computing power to search for gravitational wave signals and pulsar discoveries. Future projects might enable amateur astronomers with relatively modest equipment to contribute to cosmic acoustic research. The development of smartphone apps that can detect cosmic ray impacts, measure electromagnetic field fluctuations, or even detect very low-frequency radio waves is bringing cosmic acoustics directly to the public. Imagine a future where millions of people around the world carry devices capable of contributing to a global network of cosmic sound detection. Educational applications of cosmic acoustics are transforming how we teach astronomy, physics, and science in general. Students can now listen to actual recordings of cosmic events, use audio analysis software to study stellar oscillations, and even participate in real research projects analyzing cosmic acoustic data. This audio approach to astronomy appeals to people who might not respond to traditional visual representations of cosmic phenomena. Virtual and augmented reality technologies are creating immersive cosmic acoustic experiences that allow people to feel like they're traveling through space while listening to the sounds of stars, galaxies, and cosmic events. These technologies are making cosmic acoustics accessible to visually impaired individuals and creating new forms of scientific communication and public engagement. The potential for cosmic acoustics to contribute to fundamental physics discoveries continues to grow as our instruments become more sensitive and our theoretical understanding becomes more sophisticated. We might discover new particles through their acoustic signatures, identify extra dimensions through gravitational wave propagation, or detect evidence of quantum gravitational effects in cosmic acoustic patterns. Perhaps most intriguingly, the field of cosmic acoustics might eventually contribute to our understanding of consciousness and information processing in the universe. Some researchers speculate that the universe itself might be a kind of information processing system, with acoustic patterns serving as carriers of computation and memory. While such ideas remain highly speculative, the increasing sophistication of cosmic acoustic research might eventually provide data relevant to these profound questions. The economic and technological benefits of cosmic acoustic research are driving investment from government agencies, private companies, and international collaborations. The technologies developed for detecting cosmic sounds often have applications in telecommunications, materials science, precision measurement, and data analysis that benefit society in unexpected ways. As we look toward the future of cosmic acoustics, we're preparing to answer some of the most fundamental questions about reality itself. Are we alone in the universe? What happened before the Big Bang? Is there new physics beyond our current understanding? How did structure and complexity emerge from the primordial simplicity of the early universe? The answers to these questions might come in the form of acoustic signals, gravitational waves from cosmic inflation, electromagnetic signatures of alien technology, the sounds of exotic matter and energy, or acoustic patterns that reveal new laws of physics operating at cosmic scales. But perhaps the most profound realization is that we're becoming active participants in the universe's acoustic symphony rather than passive listeners. Our space missions are creating artificial acoustic sources as they travel through the solar system. Our radio transmissions are propagating into interstellar space, potentially creating the first artificial contributions to the cosmic acoustic environment from Earth-based civilization. In a sense, humanity is beginning to sing along with the cosmic symphony that has been playing for 13.8 billion years. Our technological activities are adding new frequencies, new rhythms, and new patterns to the acoustic environment of our local cosmic neighborhood. We're transitioning from cosmic acoustic archaeologists studying ancient sounds to cosmic acoustic engineers creating new ones. The universe has been composing its symphony for almost 14 billion years, creating layer upon layer of acoustic complexity as stars form and die, galaxies collide and merge, and the cosmic web of structure grows ever more intricate. We've been listening to this symphony for only a few decades, and we're just beginning to understand its complexity, beauty, and meaning. Every cosmic sound we detect connects us directly to the events that created it, whether those events happened seconds ago or billions of years in the past. The gravitational waves from colliding black holes carry information about matter under the most extreme conditions possible. The radio emissions from pulsars provide laboratories for testing fundamental physics. The acoustic oscillations in the cosmic microwave background reveal the recipe for everything that exists. As our instruments become more sensitive, our theoretical understanding deepens, and our technological capabilities expand, we're preparing to hear cosmic sounds that no human has ever experienced before. We'll listen to the births of the first stars in the universe, detect the acoustic signatures of dark matter and dark energy, and perhaps even hear the sounds of life and intelligence emerging elsewhere in the cosmos. The cosmic symphony is vast beyond human comprehension, ancient beyond human imagination, and beautiful beyond human description. But it's also intimate and personal, because every element in your body was forged in the nuclear furnaces whose sounds we can now detect. You are not separate from this cosmic symphony. You are part of it, made from it, and connected to it in ways that science is only beginning to reveal. Every time you listen to cosmic sounds, you're participating in an act of cosmic archaeology and cosmic communion. You're hearing the universe tell its own story, in its own voice, using a language that transcends human culture and human history. You're connecting with something far older and far larger than human civilization, yet something that is fundamentally connected to your own existence and identity. The future of cosmic acoustics will bring discoveries that we can't yet imagine, technologies we haven't yet conceived, and insights into reality that will transform our understanding of existence itself. But the most important discovery might be the growing realization that we live in a universe that is not silent, not empty, and not separate from us, but instead filled with sounds that connect us to everything else that has ever existed. As we conclude our journey through the cosmic symphony, I want to leave you with one final thought and one final question. Right now, as you sit wherever you are, you're surrounded by invisible waves of electromagnetic energy that have traveled billions of years to reach you. Radio waves from distant galaxies are passing through your body at the speed of light. Gravitational waves from ancient black hole mergers are stretching and compressing the space around you by amounts smaller than an atom. You are immersed in the cosmic symphony whether you're aware of it or not. The question is, now that you know it's there, how will you listen? What do you think about the fact that the radio static between stations contains echoes of the Big Bang itself? And here's my final question for you. If you could send one sound from Earth into space, knowing it would travel at the speed of light for billions of years and might someday be detected by another civilization, what sound would you choose? Would it be music, or speech, or the sound of ocean waves, or something completely different? Share your answer in the comments, because your choice reveals something profound about what you think is most important about humanity and our place in the cosmic symphony. The universe has been composing its masterpiece for 13.8 billion years. We've been listening for only a few decades. But in those few decades, we've discovered that we live in a cosmos filled with sounds so beautiful, so ancient, and so meaningful that they forever change how we understand our place in the infinite symphony of existence. The cosmic symphony continues, and now you know how to listen.